The word stoichiometry might sound like an odd word to describe one of the most important concepts in all of chemistry. Stoichiometry can be defined as the relationship between the relative quantities of substances taking part in a reaction or forming a compound, typically a ratio of whole integers. And you might be wondering, well, first of all, thank you for reading that to us. But more importantly, isn't there a easier, simpler, regular way of saying what you just said? And yes, indeed, there is. So let's go ahead and get started and take a deep dive into the fascinating topic of chemistry. Let us explore a very simple yet extremely important chemical reaction that has essentially led to the Industrial Revolution and the fundamental of why you and I have the lives that we do. And that is indeed a reaction that enables you to make iron from iron ore. Something as important as the production of iron is actually achieved by a very simple chemical reaction in which iron 3 oxide reacts with carbon to give liquid iron. It's liquid because it's at a high temperature, and carbon dioxide gas. But as most of you must have realized, this chemical reaction is not balanced at all. So our first task is to make sure that this reaction is balanced. So let's go ahead and accomplish that. At this point, pause the video and try to balance this on your own. My hope is that you ended up with the following coefficients. 2 moles of iron oxide react with 3 moles of carbon to give 4 moles of iron and 3 moles of carbon dioxide. And as you look at these coefficients, I want you to take your attention back to this seemingly complicated definition. However, I'm going to highlight a couple of key terms here. The first one being relative quantities, and the other one being a ratio of whole integers. And the reason why I highlighted those is because I want you to see that the relative quantities of these elements or chemicals are always in whole numbers, meaning 2 moles of iron oxide requires 3 moles of carbon, or 2 moles of iron oxide will give you 4 moles of iron, and 2 moles of iron oxide will give you 3 moles of carbon dioxide. All of these whole numbers are relative to each other, and that is a whole lot important. Without knowing these ratios, it is impossible to figure out if the reaction you're doing is proceeding the way you want it to. And this has a great deal of importance when it comes to industrial applications. For example, if you are assigned, if someone gives you 100 grams of iron ore, how much iron should you expect? There has to be a way to figure out the expected amount, right? Just like if I were to give you a recipe for 12 cupcakes, and the recipe says that you need 1 pound of flour. So I give you 1 pound of flour, and you come back with just 8 cupcakes. That tells me that something somewhere went wrong. And it is important that we're able to keep track of that, which is why stoichiometry is super important. And so being able to perform these stoichiometric calculation will tell you how much product to expect, or if you know how much product you want to make, then how much raw materials should you take. For example, if you have 100 grams of iron ore, you have to know before you start this process how much iron should you expect. If you get the expected amount, it's awesome. But if you don't get the expected amount, you know that the process needs to be tweaked. On the other hand, if you want to make 100 grams of iron, there has to be a way for you to take the right amount of iron oxide. So I know this video is going on a little longer than I was expecting, but it is super important that we understand that the entire field of chemistry and chemical reactions stands on this concept of stoichiometry. And so it is super important that we understand. Okay, so if need be, please rewatch the video, but make sure that you understand what we're trying to achieve here. Now, before we move forward with an actual example, pause the video for a second and note this down in your notebook. As you note this down, you will notice that the central point in this diagram are the moles. Moles is the language of chemical reactions. Chemical reactions are never carried out in grams or pounds or ounces. They're always calculated in moles. However, the unit that our balances know how to measure in are grams. And so there has to be a way for us to convert the grams of a substance into moles of the same substance. And we are able to achieve that by using molar mass. We have already learned how to convert grams to moles. In this example, however, you have grams of one chemical that need to be translated into grams of another chemical. So I hope you have paused and noted this down. Let's move on to the actual example. In this chart, what's given to you is the grams of A. We're calling A as any placeholder chemical. In this case, A happens to be the 100 grams of Fe2O3. Now notice how what we're trying to find is how many grams of B, which is Fe. Notice that there is no direct connection between these two boxes. So in order to convert grams of iron oxide to grams of iron, you must follow this track. How many steps will that need? Grams of iron oxide will have to be converted to moles of iron oxide. Moles of iron oxide will have to be converted to moles of iron, and then moles of iron will then be converted to grams of iron. So in total, there are 1, 2, and 3 conversions. Now that you know there are 3 conversions, the actual math is relatively easy. Our first conversion, which was grams changed to moles, was between moles of A, which is my moles of iron oxide, to moles of B, which is moles of iron. I did my second conversion, which was between moles of iron oxide to moles of iron. Now that you're armed with the basic understanding of stoichiometry and the handy, extremely useful conversion chart, let us put that information to some use. The question says, how many grams of iron will you get when 100 grams of iron oxide is treated with excess carbon? So the only piece of information that is given in this question is that you have 100 grams of iron oxide. So we will go ahead and put that underneath the iron oxide. Now here's the all-important question. If you have 100 grams of iron oxide, how much iron should you get? Notice that we know the mole ratio. The mole ratio is 2 to 4. And you might say, well, if the mole ratio is 2 to 4, which is the same as 1 to 2, a reasonable expectation would be that whatever iron oxide you start with, you should get twice the amount of iron. And I don't fault you for that. However, we must remember that even though moles and moles are interchangeable, moles of two different chemicals are different from each other because of their molar masses. Let me take you back to the diagram we just made, or the chart that we just made. Notice here that I have started off with the amount of iron oxide that was given to me in the problem. And then, just like we talked about a moment ago, there were 3 conversions. So I set up 3 conversion factors. Now, you take the unit that is given, which happens to be grams of Fe2O3, and then you will change it according to, so you will have to change this to moles of Fe. That is my first conversion. My second conversion, so I will put on moles of Fe2O3 to moles of Fe. My third and last conversion would be the moles of Fe to grams of Fe. Notice that whatever unit I had on top, the same unit is in the bottom of the second conversion. So this is a great way for you to keep track of your units and making sure that once you have all of them set up, you are able to cancel them. The only unit that you should be left with is this last one, which is the grams of Fe. Turns out that's exactly what you are trying to find. And that's how you know that you're on the right track. Now, as far as the actual numbers go, the math is fairly simple. The first thing you do is you find out the molar masses of both chemicals in question. I know that 1 mole of iron 2 iron 3 oxide is 159.7 grams. Then I know that the mole ratio between iron oxide and iron is a 2 to 4 ratio. And I know that 1 mole of iron is 55.845. Now that you have all of your units set up, all you gotta do is make sure that you're able to cancel off all the units, like so. And the only unit you're left with is the grams of Fe. So I'm going to go ahead and highlight that. That way you know that that is the unit that is needed in the problem. Now it's just a simple matter of multiplying all of your numbers. So 100 times 1 times 2 times 55.845 divided by 159.7 times 4. Feel free to leave out all the ones. They don't really matter. I just wrote them because of habit. Okay, so just go ahead and do the math and figure out the answer. Pause the video and then check if you got the same answer. If you did the math correctly, your answer should have been 17.48 grams. Now let's pause for a second here and really think about what does this answer mean. It means that if you start off with 100 grams of iron ore, which is iron oxide, it contains 17.48 grams worth of iron. So you need a whole lot of iron ore to get a relatively small amount of iron metal. which makes sense because iron is just a small part of this whole formula. So if you start off with 100 grams, you should get an answer that is significantly less than the mass you started off with. So not only is it important that you check the answer, that you check your math, that you check your unit, but when you get the answer, try to make sense of it. Make sure that it makes sense, that the answer you got matches up with the amount that you started to begin with. I know this is a lot of material. I do not expect, and neither should you, to learn all of this after watching this video once. Some of you might struggle, and that is perfectly okay. There is no alternative to learning stoichiometry than practice, practice, and practice some more. Okay? So make sure that you practice a lot of problems. If you have any questions, feel free to get in touch with me, and good luck.